Hey everyone, I'm Brix, and this is Holly, and we're software engineers on Google's open source security team, with the goal of making open source secure at scale. Specifically, we work on a group of projects labeled OSV, or Open Source Vulnerabilities, which helps open source developers manage and fix known vulnerabilities in their dependencies. Today, we'll talk a bit about what OSV is, why vulnerability management is important, and then go over some of the interesting challenges we found while working on this project. So, what is OSV? OSV includes the OpenSSF OSV Schema, a format for projects to publish their vulnerability advisories so that it's easy for others to consume. The OSV.dev database, which aggregates all the OSV formatted advisories that's been published by the community. And OSV-Scanner, which uses that data to scan your project dependencies for vulnerabilities. Let's first cover why managing vulnerabilities in dependencies is important.
The reality of software development in 2024 is that even small projects have a massive wave of dependencies. It's important to focus on keeping your own code secure, but managing vulnerabilities in your dependency is absolutely critical. Think of like this: a flaw in your own code needs someone to target you directly. But a popular dependency with a vulnerability, that's leaving your door wide open to automated attacks that scan millions of sites, hoping to find an easy way in. So the concept of identifying known vulnerabilities in your dependencies sounds really simple, right? You get a list of dependency versions, and just look up whether each dependency has a vulnerability in some database. Well, it turns out this is not so easy.
To break this down, we found several categories of challenges when it comes to identifying what dependencies are actually vulnerable. These are getting good quality data sources for your vulnerabilities, matching vulnerabilities against packages for each ecosystem, and how to prioritize and remediate those found vulnerabilities in an efficient manner. Let's first start with getting good quality data sources. CVEs are how most vulnerabilities are publicly reported, but CVEs have limitations when it comes to automating the process of finding vulnerable dependencies in your project. The main way CVEs are matched against packages are via CPEs, which are manually added by the folks at MVD. While it provides a unique identification of the package and version, it's really hard to map it to the actual open source package in the ecosystem. Example of this is this npm package, CK editor. This is just the first npm package, npm CVE I found while building these sites. And you can see that the CP name, which I circled in red, simply doesn't match the naming npm. And there's no way to predict what the CP name of this package will be before the CPE is published. So to get around this issue with CVEs, many vulnerability scanning tools maintain their own proprietary databases where CVEs are used as a reference, and they build their own structured data on top to aid with precise package matching. With the OSV and OSV schema, we wanted to do something similar and define a structured format, but create it as an open standard where everyone can contribute and use the data however they want. Here is what it looks like. It's a JSON format designed specifically for describing vulnerabilities in open source software. It solves the package identification problem that CVEs had by requiring the affected package name and version follow the conventions of the specific ecosystem. Both our team and the community publishes advisories enriched with the structured data of exactly what packages at what versions are actually affected. We host all these enriched advisories on our site OSV.dev. This is a federated database where the contents are almost entirely made by the community. We just aggregate and index them for easy querying. And all of that logic is also open source, so you can host your own version. The OSV format is now pretty widely adopted, covering over 20 ecosystems, with many ecosystem security advisories on board as well as publishers. Some notable ones being the GitHub Security Advisory or the Go Security Advisory. And because the ecosystem advisories are publishing OSVs directly, we can go even further and specify symbol-level information in a structured way in the advisory. For example, this Go advisory has exactly what functions are affected. This is very useful to cut down on false positives when we start matching against dependencies. And while we're building OSV-Scanner to use all this vulnerability data to match it against your dependencies, we discovered some interesting challenges to vulnerability scanning, which we'll go over.
The first step to matching your vulnerabilities to dependencies is to check the log files. Log files like Go mode for Go project act like a detailed inventory of all our dependencies, including indirect or transitive ones and their versions. By comparing these versions against a vulnerability database, we can see if our project is secure. For example, this Go mode file is using Go version 1.21 with just 2 dependencies. So what we need to do is just simply check if those dependencies have known vulnerabilities by querying a vulnerability database, such as the OSV API, right? Well, unfortunately, things get more complicated in the real world. Log files are not always that straightforward when showing the versions of our dependencies. In the Go ecosystem, there are quite a few intricacies to consider when parsing log files. For example, it's important to note that vulnerabilities might exist within the Go standard library, just like other packages. The standard library version is linked to the Go version you use during the build process, and the Go version you use might not be the one specified in your Go mod file, because it depends on the Go version installed on your local machine. Additionally, Go toolchain directives can also modify the Go version during the build process. In our example, we also have a replace directive modifying a package version. This replace directive substitutes a dependency with a local module, and we can't tell its final version from this Go mod file. So figuring out what will be inside your Go binary when building can become a bit of a puzzle. Compared to other ecosystems, Go is still relatively straightforward. Let's look at another more complicated ecosystem. For Maven, we have POM XML files to define dependencies for Java projects. However, it's not as easy as in Go to determine the exact version of dependencies. Let's go through some of the complexities in parsing this file. First, unlike Go, Maven doesn't have a standard log file, so transitive dependencies are not recorded in the POM XML. To find the actual packages included during compile time would require querying the upstream repositories. And even direct dependency versions are not easy to get. Versions could be defined and replaced by properties, which requires us to perform variable substitution. Versions can also be defined in the dependency management section instead of the dependency section. Moreover, dependency management can be inherited from multiple files. Here, we're using a local parent file to define some package versions. This parent file could also have been placed on a remote server. Furthermore, the Maven ecosystem is decentralized, so there could be hundreds of different servers that could be hosting packages. And we can't even always trust the Maven documentation. When there are multiple versions defined for a single dependency, the documentation specifies the first declaration wins, but the actual Maven tool will always pick the last one. When we were building OSV-Scanner, we discovered this ecosystem complexities appears not just in Go and Maven, but in almost all the ecosystems.
And log files are not the only thing we need to scan. It is now ubiquitous practice to deploy your code into containers. As new vulnerabilities can show up at any time, even without any code changes, continuous scanning of your deployed containers can tell you when it's no longer secure, and you should redeploy with an updated version. Vulnerability scanning of containers is different from scanning project log files in at least 2 major ways. First, you have an entire operating system to scan instead of just a specific folder, which means a lot more files to scan and a lot more potentially conflicting sources of information. And secondly, many containers store only the final build artifacts, which often contain less information than what the source code can provide. We found that different scanners often handle this quite differently. We compared the results of some popular scanners against each other for a single project, and also when the project is built and deployed into a Docker container. You can see when we're just scanning the project by itself, the results between scanners are quite consistent. But when we switch to scanning in a container, we can immediately notice some interesting stats. First, the number of vulnerabilities explodes to up to like 3 digits for quite a few scanners. And also the vulnerability results vary by quite a bit. Most of these new vulnerabilities are just from the latest version of the Go stable slim image, or from installing the Golang compiler and its dependencies, which you would think is secure, but they remain on older versions to remain stable, and those has many open vulnerabilities. These vulnerabilities might not actually affect you, but that's a story for another time. For now, let's focus on some of the reasons why the results can differ.
The difference could be caused by how log files are handled. For container scanning, we need to shift our focus away from log files and towards directly analyzing artifacts. While artifacts contain less information than log files, the information is more accurate, as log files don't always reflect what's actually installed. By examining artifacts themselves, we can get a better picture of our deployed dependencies. If we also scan log files, this can lead to potential false positive or duplicate results. Another reason the results can vary is because vulnerabilities in the standard libraries of language are handled differently. Some scanners show them as vulnerabilities on the compiler package itself, while others will show the same vulnerability twice, once on the compiler package and once on the build binary. OS packages also need extra care when scanning. With OS packages, we need to pay special attention to the OS version and the upstream source version. Sometimes when we install packages directly from the OS, such as using apt install, the version we get isn't the original upstream release, but a version patched by the OS maintainers. For example, let's say we have the Python 3 Django package on Debian 11. A scanner could find pip's metadata file for this package. It could parse that to get the package version, which will display as 2228. However, since Django has been installed as an OS package, it could have been patched. If we look at Debian's metadata file, we can see the actual version is Debian's modified version, not the official 2228 Django release. So to get the most accurate results, we need to compare against the Debian specific version here, as it may include some fixes not present in the upstream release. These are just some of the interesting examples we found when trying to understand why scanners produce different results. And this is just for Debian containers. Other distros or OSs will have their own challenges. Scanners can also report an overwhelming number of vulnerabilities, which brings us to our last topic, prioritization and remediation.
As you saw, even on the latest version of an image, you can easily get double or triple digit vulnerabilities. So if you're working on a large code base or a slightly old or legacy project, at this point, you'll probably get a giant list of affected packages and vulnerabilities and get quite overwhelmed by the sheer number of results. Ideally, you will want to update and patch everything, but most of the time, this is simply not possible given the time required to do so. You want to be delivering features, right? You don't want to be updating dependencies, which is why we need to provide developers a way to prioritize and prioritize what vulnerabilities to fix. One option is to perform the reachability analysis with the symbol level information I mentioned earlier. By checking the call graph to see if you actually call a vulnerable function at any point, we can deprioritize the uncalled vulnerabilities, allowing you to focus on fixing the ones currently affecting you. Here is an example of OSV-Scanner detecting you're not using a vulnerable function in a Rust project. Another way to avoid getting overwhelmed by vulnerabilities and end up doing nothing is to prioritize by the time investment required to fix. Let's say you have 100 vulnerabilities in total, and to fix them, you need to spend 10 hours. Obviously, it's best if you can fix all 100 vulnerabilities, but if you only have, let's say, 2 hours, it's much better to know the best course of action you can take in those 2 hours to resolve the most number of vulnerabilities. We're calling this concept guided remediation. The idea here is we calculate all the package updates required to fix your vulnerabilities, and we present them to you piecemeal, with options ranging from just bumping up all the minor versions within the version constraints for minimal breaking changes, to completely recalculating your dependency graph, to even ordering the major breaking version updates by the number of vulnerabilities resolved. So in some cases, you only need to make 1 or 2 breaking upgrades out of your hundreds of dependencies and resolve, let's say, 90% of the vulnerabilities being reported. So if these features and challenges sound interesting to you and you want to try our OSV, have a look at our project on GitHub and feel free to contribute as well. No? Next question?
Thanks. That was a fantastic overview of OSV. Question on what you've learned from the quality of the data. So 20 plus years of CVE, and we still have huge variation, even from Fortune 50 companies, about whether they are producing the required minimums, less, or having all sorts of extra data. How many of OSV records actually give you, for example, function level data, and how many of them are just, I think this is a problem? Oh.
Yeah, so for CVEs, I think we have some spreadsheets I can share with you later for like, specific information. But for OSV specifically, like function level data, that only exists in like 2 ecosystems right now. Like Go and Rust are the 2 popular ones. There are some in Java I noticed, but like those are like single-digit numbers of vulnerabilities in Java that has that information. For OSV, I think we try to keep like the exact version of what's affected like quite clear in the record, and we like check that as we're importing them to make sure they're clear. Yeah, I hope that answers your question.
Sorry,
Yep.
just a quick follow-up. So you are doing sort of MVD-like manual data curation?
We're not doing manual data curation, but we have automated systems that check that we actually enumerate like the versions, and then they give you actual versions. Is there a question back there?
Real quick, if I missed it, I'm sorry. Would the MVD impact what's going on there? Is that impacting your tool?
Yes, in a small way for C and C++ advisory specifically. For those things we import from CVEs, and because without the CPE data that MVD provides, that does impact us. But for other ecosystems, we pull straight from either their advisories specifically, like the Rust advisory publishes directly in OSV, or we pull from like GitHub security advisory, and those I don't think are impacted. No? I personally have not worked with Bazel, so I can't really share that much on that.
I can answer very briefly. Bazel does not do a great job of packaging ecosystems yet. It's a work in progress. For a single source tree, the dependency graph is now managed directly inside the source tree. So Bazel or Bazel, and that's it. Does an amazing job of tracking changes to the dependency graph and doing minimal updates within a mono repo. When you wander into the world of package ecosystems, it's a little bit more complicated. Most of you should be doing a mono repo. You're not that big. People assume that you are. But it's always more going for this problem.
Cool. Yeah. Thank you for listening.